previous lecture we covered this correlation receiver. One of the things that, this is kind of coming straight from the theory. This is what theory says how you should demodulate. The theory doesn't see one practical problem. And the practical problem here is this basis vectors have to be exactly the same ones as they were in the transmission, right? Think about what do we use for transmission. I have in the upper branch I have cosine. So this means this needs to be cosine 2, right? Well, it cannot be cosine 2 pi s c plus some phi. It cannot have phase shift relative to the original cosine. Why? Because if I take the phase shift, we're running into the same problem we had with double sideband AN. This guy needs to be synchronized to that guy at the transmission, right? And that's not an easy task. Although we can encode, differently and make that easier, but that synchronization is quite a challenge. And then the other challenge is, okay, this sampling needs to occur right at the boundaries of my symbols, right? How do I detect where those boundaries are? So both of these challenges need to be dealt with, and they're dealt with in great detail in every practical organization. In your book, you have quite a bit on both of these subjects. Right now, I just wanted to point out, and we just move on to the next receiver architecture. But in digital communication, if you take that course, we're going to talk about these two in more detail. Now, alternative type of the receiver is what we call matched filters. So let's look at that one. So type 2 demodulator. This is matched filter. Okay. So we're still number 1 out of the 2 tasks. First task is demodulation, so we need to translate R of t into a point in the signal constellation space. We can do that using correlation receiver, or we can use that, do that by using a matched filter receiver. So to understand what matched filter receiver does, consider the following. Consider a task that is done by this correlation receiver. Rk is determined as integral from 0 to t, R of t, or let me use tau here, psi k of tau d tau. So this is what my correlation receiver does in every branch. The signal R of tau is the same, but then it gets multiplied and integrated depending on which branch you are. Now, suppose I can design a filter. So just a passive device here that I feed R of t, and in general case it gives me an output Y of t. But I want to sample this output Yk of t, and I would like that to be the same as this Rk. Because remember, Rk is just a constant, right? So let's see if we can come up with a filter that will do the same thing as the correlating receiver. Why is that beneficial? Because if I come up with a filter, then a filter is a passive device that just sits there. No need for locally generated oscillators, no need for synchronization at the phase level. So this gets rid of this problem here, right? I still have to deal with the problem how to sample at the correct time, but that's a much easier problem to deal with. So let's look at what happens here in the output. We know that this Yk of t, this is now general linear system theory, is R of t convolved with Hk of t, right? This is always true when you have a filter with given impulse response. Now, this is an integral from 0 to t, R of tau, Hk of t minus tau d tau. Right? That's our convolution here. And let me sample this Yk at t. So Yk at t becomes an integral from t, 0 to t, R of tau, Hk of t minus tau d tau. Now, we need to compare this and this. And we can see that if we can make hk of capital T minus tau same as this phi k of psi k of tau, then we actually accomplish the task. I have a filter that does the same thing as the correlation branch of a correlating receiver. So comparing star, double star, we see that hk of capital T minus tau needs to be the same as psi k of tau for t in interval 0 to t. That t I'm going to send. So, okay. If that's the case, if I make this hk of t minus tau the same as psi k, you can see that yk of t becomes the same as the rk. Okay? And this filter essentially performs the dot product that I want to happen in each one of these branches. Now, what does this mean? hk of t minus tau is the same of psi k of tau. Let's let's say that this is my psi k of t, and let's say this thing looks, let me see how I have it. Let's say my basis vector looks somewhat like this, between 0 and t. Then how does my the impulse response of the matched filter looks like? Well, it exists over the same interval from 0 to capital T. It is flipped. Why is it flipped? Because you can see if this one is function of tau, this one is of minus tau. So it's flipped and then delayed by capital T. So if you flip this, you end up with this response, and then if you delay it by t, so this is this kind of implied. So this is hk of t, the impulse response of the matched filter. Okay. Why do we call this filter matched? Because its response is matched to the signal itself, matched to the basis vectors that you use for signaling. Okay. So how would the matched filter receiver look like? Well, matched filter receiver or demodulator. You have your R of t coming in. Now you have all of these filters that have impulse responses that are matched to your basis vectors. So this is h1 of t, h2 of t, h3 of t. They're just sitting there. They're passive devices that are not requiring any particular synchronization. And then you have a sampling here that samples the output of this filter at kT. And what you're going to end up here is R1, R2, Rn, R1 being Sn1 plus N1, this being Sn2 plus N2, this being Sn plus N capital N. What are the advantages of, let me just list them here. So mesh filter is a passive linear device. Right, so that's a really big advantage when it comes to implementation. No need for multiplication, right? Because multiplication is inherently non-linear process. You know, that's the source of a lot of trouble in the practical receivers, because this is done in a device called mixer, and mixer is non-linear device. It has to be to do multiplication. And then no need for carrier phase extraction, right? And this is again the same reason, because now you need to extract, in that one you need to extract the phase of the carrier, because you need to do a multiplication with the proper signal with the proper phase. Here, you know, these are passive devices that that have proper response whenever you hit them with a signal. Okay, so that's how. But what I want to stress is this: regardless of which one of these you have, mathematically they're doing the same thing. What are they doing? They're taking the input signal, projecting it along the directions of the basis vectors, and producing an output vector which has the coordinates associated with that signal r of t, right? So mathematically they're doing the same thing. Practically, in modern receivers, both of them are implemented in software, and since they do basically essentially the same thing, then it's really hard to say which one you're implementing, right? They're essentially the same, right? So mathematically, these two are the same, and in a lot of practical applications, they're the same as well. Okay, so one thing that I haven't discussed yet, and this is where the next discussion is coming. I kind of gave you one way, and I said, well, how are we going to translate this R into vectors? Well, let's project, right? And we saw that this gives us some sort of result. Now, the legitimate question to be asked is this. First, is this the only way, right? Is there an alternative way how I can do this? And if this is not the only way, is it the best way? Can I do it better than this? And what we're going to spend a couple of boards here showing is that this way is the best possible way to do this, right? Which is very important to know. You know, these kind of results are very, very important for us because they save us tremendous amount of time, right? The guy who proved that perpetual model is not possible saves tons of work that would have been there, you know, people trying to make one, right? It's the same here. You know, we have a filter, we know how to demodulate. There's a hanging question, can you do it better? And what we're going to now demonstrate is that meshed filter is the optimal way of receiving the signal, optimal way of demodulating the signal in AWGN. Right? So let's look at some of the properties of the mesh filter, and this is going to be one of the most significant properties. Yeah, it's the best filter for the task. So properties of mesh filter. I guess I have a title properties, but I don't know if I even have a multiple of them. I just have this one property that's the most significant. Yeah, so let me just state for this property. If S of t is corrupted by AWGN, so I'm receiving the signal in AWGN channel. The filter with the response that is meshed to S of t, maximize signal to noise ratio at the output. So essentially, it's the best filter for the job. And what is the job? The job is demodulation. So this is the best way to demodulate the signal. Here's what we have. We have R of t. Now I have here my mesh filter, H of t, and then here is the output Y of t. Now, a couple of remarks. First, I dropped M here, right? Because we have M individual branches. So in every one of them is processed independently. So I just dropped it for the sake of simplifying notation, right? So this is the same, what I'm going to go through here is the same thing happening in every single one of the branches. So what is it that I'm trying to demonstrate here? Well, first I'm going to define what the signal to noise ratio of the output means. Right? So we're going to define what is the signal, what is the noise. And then we'll find out that this signal to noise ratio is going to depend on the filter impulse response, which it should, right? And then I'm going to say, well, can I search through all possible filters and find out which one is the best one? And I'm going to do that search, and what will come out as the best possible filter to maximize the signal to noise ratio is going to be the matched filter. Then, as a result of that, I'm going to be confident that the best way to demodulate is to use the matched filter. The filter whose impulse response is matched to whatever is the signal that you're trying to receive. So, in general, this is how we start. This Y of t is going to be your R of t convolved with H of t, which is an integral from 0 to t, R of tau, H of t minus tau, d tau, just the definition of the convolution. In our case, this is integral from 0 to t. This R of tau is essentially S of tau plus N of tau, right? I have both signal and noise coming through this filter. And then I have H of t minus tau d tau. If I split this integral, I have y of t is integral from 0 to t S of tau times H of t minus tau d tau plus another integral from 0 to t N of tau times H of t minus tau d tau. And you can see, you can recognize this is still little t, sorry about it. Okay. Now you recognize what this is. This is a signal part. And this part here is attributed to what? Noise part, right? So both signal and noise come into the input to this filter. Whatever comes at the output will have two components as well. Why? The filter is a linear device. The superposition holds. The output response is equal to the sum of the responses to the individual components of the input. So now if I sample this at time t equal to capital T, at t equal to capital T, I get y of capital T is going to be integral from 0 to t s over tau H of capital T minus tau d tau plus integral from 0 to capital T N of tau H of capital T minus tau d tau. Okay. So you get the sample of the signal, which I'm going to call ys of t, and then the sample of the noise, which I'm going to call y n of t. Right? Ys of t is the signal, and this part here is noise. Okay? Now, let me define the signal to noise ratio. The signal to noise ratio in the output SNR output is going to be defined ys squared of t divided by expected value of yn squared. Okay, so this is what I define as a signal-to-noise ratio. Notice how I treat these two differently, right? One is the square of the signal, and the other one is the expected value of the square of the noise. Why is that the case? Well, this S of t is always the same signal. So every time, this part is going to be the same. So expected value is not a random variable. It's a predicted output of this filter. Because the signal is known, I always signal with this S of t. And if the filter is known, the output is known all the time. So this is always going to be the same. However, noise is a random process. So even though the filter is known, every time I'm going to have a different output because the random is. So I'm looking at the expected power of the noise downstairs and the power of the signal upstairs. So what does this filter do? Let's just think about it. The signal and noise are coming in. I'm filtering these two. You can let's just get some intuition here. If this filter is, let's say, doing nothing, right? It's just all pass filter. What's the signal to noise ratio of the output? No. What is? Think about it. You have a signal. Put its Fourier transform, right? Or power spectral density. You have noise. If the filter lets everything go through, what's the signal to noise ratio of the output?
It's going to be the signal over the noise.
Is what? The signal has a finite energy, finite. Noise has infinite. So what's the signal to noise ratio? 0. Right. So the filter needs to, kind of be narrow. It needs to let the signal go through. So this filter, whatever comes as a result, will not extend beyond the signal, right? Because everything it lets in, that's beyond the signal power spectral density is just going to increase the power of the noise, right? Now you say, well, can it be an ideal filter, right? That has the same bandwidth as the signal. That's a good candidate, right? And that one would recover the shape of the signal in the best possible way. Would it maximize signal to noise ratio? That's the question, right? So so what is it that I'm looking for? I'm searching for age of t to maximize this, okay? And we'll come up with a very interesting result. Once we get to that point, we'll have to stop and think a little bit about what does this result tell us, right? Because it's a little bit against what we've learned in analog communication. It's going to be qualitatively different. Okay, so let's now look at this. Okay, this is, I want to maximize top, minimize the bottom, so that I maximize this particular ratio. So first thing, this ys squared of t is going to be an integral from 0 to t, s of tau, age of t minus capital T minus tau, d tau, everything squared. There's nothing to be said here. This is it. When I select h, I get ys, for any given selection of h. Let's work on a bottom part here. Expected value, yn squared of tau, of t, sorry, is expected value yn of t times yn of t. How smart is this, right? So, but then I decompose this. I say this is expected value yn of t. I'm going to write this as integral from 0 to t n of tau 1, age of t minus tau 1, d tau 1, times an integral from 0 to t n of tau 2, age of t minus tau 2, d tau 2. Right? What did I do? I took these samples and I replaced them by convolution. I used a different running variable, tau 1 and tau 2, because I want them to be different, but because you can sense, right now I'm going to merge these two integral and integrate over both variables at the same time. So this becomes an integral when tau 1 goes from 0 to t, integral when tau 2 goes from 0 to capital T, and then I have the expected value of n of tau 1, n of tau 2, age of t minus tau 1, age of t minus tau 2, d tau 1, d tau 2. Now, my noise is AWGN. So what that means, I know this quantity here. What is this quantity? Expected value of this. How do we call it? It's a little bit disguised, right? We call this autocorrelation function, right? What's the autocorrelation function of the noise? Here's what we said, autocorrelation function. So, we have for the thermal noise expected value on n of t minus tau. This was r of tau, right? And if I now realize that the noise is a stationary process, and then this depends only on the difference between t and t minus tau, then this thing here becomes autocorrelation function of the difference of these two, right? Because really, all that matters here is the difference between them, right? So I can, all right, so, but what is, I know the actual value for this. From the Wiener-Kinching theorem, what do I know about autocorrelation function? It's an inverse.
It's the Fourier series of
Is what?
the autocorrelation function. I mean the RTL. It's the Fourier series, right?
It's an inverse Fourier transform
Yes,
of
Fourier.
power spectral density.
Yes.
So what is the power spectral density? N0 over 2. So constant. So the inverse Fourier transform of constant is delta pulse. Right? So this is now N0 over 2 times delta of tau. That's the Fourier transform of the power spectral density. So our power spectral density is as N0 over 2. Autocorrelation function is N0 over 2 times delta of t. So this here is equal to N0 over 2 times delta of tau 1 minus tau 2. Okay? Now, you know, wherever these complicated integrals happen, delta comes to our to savings, right? So this appears to be a double integral, but it really only exists when tau 1 is equal to tau 2. So here's what you're essentially saying that you're integrating. You're integrating tau 1 goes from 0 to t, and then tau 2 goes from 0 to t. But the only place where this is what you're integrating is different than 0 is along this line, right? When tau 1 is equal to tau 2, right? Do you follow? Yeah. Because of this. This will make everything equal to 0 when tau 1 is different than tau 2, right? So although I'm integrating over this entire square, practically I'm integrating only along this line. So let me say like this then. Tau goes from 0 to t. And then this here is N0 over 2 delta of tau times h of t minus tau d tau. And then this, I can say squared. Actually, I don't need to, it's either, yeah, because this is, sorry. So So this is n0 over 2 h squared of t minus tau d tau. Okay? So that's the value of this integral. So now I have my ys, and then I have my yn, expected value of yn. Let me form the signal to noise ratio. So therefore, signal to noise ratio at the output becomes what I have up there. So it's 0 to t, s of tau, h of capital T minus tau, d tau, and then 2 downstairs and 0, integral from 0 to t, h of tau minus t, d tau, but I have to square it. So that's my signal to noise ratio. So what does the signal to noise, what does this expression tell me? Well, the only thing now that I'm looking for is h. Give me an h, I'll tell you what the signal to noise ratio is in the output, right? Just plugging it's a little bit strange equation, right? Because the unknown is a function, right? It's not a variable, it's not x, right, that you're looking for. You're looking for a function of time for which this value here is maximized, right? How many candidates do I have? Infinite many, right? So I'll have to search through this space of all possible choices for h. How do I search for that? Well, let me introduce one important result. You know, it has one of those names that consists of several people that actually invented this, or discovered it, I should say. In English literature, we're kind of lucky because it has only 2 names. When I studied this, it had 3 names, but the third one was really difficult to pronounce. Right? So it's called Cauchy-Schwarz inequality. Cauchy is the same guy you remember from calculus, you know, long time ago. So what does this inequality say? Now, even though you let me go through it, and then I'll show you. It's your old friend. You know it from elementary school. You just didn't call it that way in elementary school. Right? So let me just state it here, and then I'll show you where does it show up in elementary school. So here we have 2 functions on interval I. G1 of t and G2 of t, right? So just arbitrary functions on this interval. Well, it can be shown that this holds true. G1 of t in dot product with G2 of t, magnitude squared, is smaller than the norm of G1 of t squared times the norm of G2 of t squared. So the dot product between 2 functions is smaller than the norm of the 2 functions squared. If I write this in an integral form, this is what I have. Integral from 0 to t, or I should say over interval I, G1 of t times G2 of t dt, everything squared, that's a dot product squared, is smaller than, what is the norm? The norm is the dot product with itself, G1 of t squared dt, and take a square root, but since I have a norm square, I don't have to take a square root, times integral over I g2 squared of t dt. So this code, it's called Cauchy-Schwarz inequality. More, I guess, a lot of times it is referred to as triangle inequality, right? And it is essentially, we all, let me just give you a secret, we all know that these functions can be seen as vectors. So we represent them as vectors. This is a vector A. Let me just map these into vectors. This is A, vector A in dot product with vector B, magnitude squared, is smaller than A times B. Right? How do I know that this is case? Well, A in dot product with B is A times B times cosine of the angle between A and B, right? Okay? And this, if I take the magnitude square of both sides, then I get that magnitude A dot B is equal to magnitude of A squared, magnitude of B squared, times cosine squared of the angle between A and B. And this is always smaller or equal than A times B. Right? That's our triangle inequality. And that's what this complicated inequality states. Now, what is of great interest to us is, when is it equal? When these two sides are equal? What happens to
Cosine.
cosine needs to be, when is that the case? Because the angle in between A and B is what? 0. So what do we say about these two vectors when the angle is 0? They're parallel, right? So the equality holds if g1 of t is parallel to g2 of t. When it comes to functions and vectors too, that means g1 of t is equal to some constant times g2 of t, right? They are parallel. They are the same, just have a different constant multiplier. We have everything now that we need. So let's go back to our signal to noise ratio that I have here. So going back to our signal to noise ratio, this is where we start. We say signal to noise ratio is 2 over n0, integral from 0 to t, s of tau, h of capital T minus tau, d tau, divided by integral from 0 to t, h of capital T minus tau, d tau. Let g1 of t, g1 of tau, be equal to s of tau, and g2 of tau be h of t minus tau. All right, so I'm kind of trying to apply this inequality that I have here, essentially this. Now, signal to noise ratio and the output has to be smaller or equal than 2 over n0. And then upstairs I have a dot product. So instead of this dot product, there's a square here, right? Instead of this dot product, I'm gonna actually, see, you should have corrected me here. This needs to be squared, right? Right, because I have ys squared over expected value of yn squared. So I need to have this square divided by this, right? So here, therefore, I have this square. So now, this dot product, if I look at this, this fits this description, right? It's a dot product of the two functions squared. So it has to be smaller than the norm squared of the first and the norm square of the second. So the norm square of the first is integral from 0 to t, s squared of tau, d tau. Norm square of the second is 0 to t, h of t minus tau squared d tau over integral from 0 to t, a squared over t minus tau d tau. Okay, so it has to be smaller than this, it cannot be large. This is the largest it can be, the best I can do. Now, what is this value? Well, look at this. This and this cancels, right? This is our good old friend. Integral from 0 to t s squared of tau d tau is what? It's if I have a signal from 0 to t, and I square it, and I take the area under the curve. Energy, right? So this is the energy of the signal. So this thing here is 2 epsilon f over n0. So here, look at the thinking here. It says this is the signal to noise ratio of the output. It is always smaller or equal than this. So the largest it can be is it is equal. When is it equal? When these two are parallel, right? So the equality holds when h of t minus tau is equal to k times s of tau. Well, what is this? When my filter is matched to my signal, right? So let me just summarize in a couple of sentences, because there's a lot of math here, and I'm afraid that we might lose this. What is it that we're trying to do here, right? So we start by saying, okay, I'm searching for the filter that will maximize the signal to noise at the output. So I say the filter has an impulse response h of t. I go through the motions, and this is my output that comes from signal. This is the output that comes from noise. So I've defined the signal to noise ratio as this one squared divided by expected of the noise squared. And I realize that the noise is wide, so I end up with this expression here. Okay? It says this is what the signal to noise ratio looks like for any given filter. You give me filter, I'll tell you what the signal to noise ratio is going to be. Right? Age, once you know age, you know everything. Now I say, I'm looking for a filter that will maximize this. Well, I say, okay, I know this, that this is always smaller than this expression here, right? And this expression is, you know, I use Cauchy-Schwarz inequality to separate this into two integrals here. But I know signal to noise ratio is always going to be smaller than whatever I get here. Maximum is going to be equal to this. And that maximum is going to occur when my two functions, s of tau and h of t minus tau, are parallel. So that gives me what h should be, right, to maximize the signal to noise ratio. Out of all possible h's, this is the one that maximizes, the one that's parallel to the signal. And that's my mesh filter, okay? So the mesh filter is the best you can do. That's the summary of all of this discussion. Right? It's important to go through this to realize how you get there. But at this point, we just summarize. You know, you're going to pass your signals to the mesh filter, and you're going to be confident that what comes at the output is maximizing your signal to noise ratio. Therefore, it's maximizing your chances of making a good decision, right? Because you're making a decision based on what you see after this filter, right? And if that rejects the most noise, then your chances of getting a good decision is improved. Now, what you need to remember is this result here. At the output of the match filter, your signal to noise ratio is always this. Always, right? So that comes very handy in exam scenarios, right? Because a lot of times you say, what is the output here? And instead of going through the convolution and kind of chancing that you're going to make some mistake with integrating, if you have a signal and you know that you're demodulating with matched filter, no need to integrate. Just calculate the energy of the signal, multiply by 2 and divide by power spectral density of the noise, and you're there. That's what it is. All right. So now, let's. So that's a very important result, but it is somewhat confusing. Let's look at it from another angle, kind of on the basis what we've done in analog communication. So this is what I just said. You have S of t. It's corrupted with noise N of t. And then you're demodulating this with a matched filter. So you have here H of t that's matched to the signal. You're sampling this at kT. What comes out here has a signal to noise ratio at the output, which is 2 epsilon s over 0. Now this H of t is given as S of t minus t. So it is matched to your input signal. And N0 over 2 is the N0 over 2 is double-sided power spectral density. Double-sided power spectral density all times. So that's all of this math, kind of lucky for us, boils down to very, very simple final result. That if you have S of t, it's corrupted with AWGN, with N0 over 2 being the power spectral density. You are putting here the matched filter. When you sample, the signal to noise ratio is going to be 2 epsilon s over N0. Now consider a frequency domain, because I want to show you a frequency domain. Because it's more insightful. This whole concept of flipping and delaying is a little awkward, right? What is it that you're doing? Seems like somehow feels like we're cheap or something, right? Why would anybody come up with, delaying the signal and then flipping it over? Why would that be of any usefulness, right? So let's look at the frequency domain view of this, and then it becomes really crystal clear what is the mesh filter actually doing. So H of f, which is Fourier transform of your H of t, essentially your frequency response associated with a mesh filter. We know by definition that t goes from minus infinity to plus infinity. H of t, e to the minus j, 2 pi ft dt. Now in this case, since my H of t is matched to the signal, I can write this as an integral from minus infinity to plus infinity, s of t minus t, e to the minus j, 2 pi ft dt. Right, what did I do? I realized that my signal here is matched to my filter is matched to the signal, so I just substituted the impulse response of the filter as expressed as the signal itself, right? So here I need to integrate this. Let me introduce the substitution. T minus t is some nu. Therefore, d nu is minus dt. And I'm going to be needing t here, so t is going to be equal to nu plus, t is going to be capital T minus nu, right? So when I substitute this, H of f becomes when here t goes from minus infinity, where is nu? If this is in minus infinity, where is nu? Plus infinity, right? So nu goes from plus infinity to minus infinity. S of nu e to the minus j 2 pi f, and instead of t, I can put t minus nu. T minus nu, and then this dt is minus d, right? Minus d, right, instead of dt. So if I rearrange this a little bit, you can see that this minus here is going to flip the borders back. I can take e to the minus j 2 pi f capital T outside because it does not depend on nu, right? So I end up with integral nu goes from minus infinity to plus infinity, s of nu e to the j 2 pi f nu b nu e to the minus j 2 pi f t. What is it that I have here? Now, if I were to put minus here, what is it? It's a Fourier transform of what? Of S. So because there's no minus, I can put it here, and I can put complex conjugate, right? To flip it back. So this is essentially S of F complex conjugate e to the minus j 2 pi f t. So that's the frequency response of my filter. So let's take a look at now what happens with frequency. This is f. This is my noise. Noise has power spectral density n0/2. It's constant across the entire axis. This is my signal, right? So this is S of f. How does my filter look like? What does the magnitude response of my filter look like? Magnitude response of the filter is magnitude response of S of f, complex conjugate. It's the same as the magnitude response of signal itself. So how does my filter look like? It has the magnitude response, which kind of follows the signal, right? So, like we said at the very beginning, what is the response of the filter outside of frequency content of the signal? It's 0, right? It's rejecting. Wherever it's only noise, it's rejecting, right? Because its response goes to 0. So all of this noise is filtered out, right? Now, when it comes to the portion where there is a signal, what does the filter do? Look at this portion here. Here the signal to noise ratio is large, right? The signal power spectral density is much larger than the noise power spectral density. What does filter do? It amplifies that area. So when it's good, it gets amplified. When I'm in this area here, where the signal to noise ratio is poor, what does filter do? It attenuates that area, right? So it's kind of like this is how the filter thinks. I have this signal spread over frequencies and noise spread. Noise is uniform, so I'm worrying only about signal. There are portions of the signal band where the signal to noise ratio is good, and there are portions of the signal bandwidth where signal to noise ratio is poor. If my task is to maximize signal to noise ratio in the output, I'm going to take the good portions and multiply them, and I'm going to take the bad portions and I'm going to attenuate. And I'm going to be 0 everywhere my signal is 0, because there is no need to run this through. So you can see it's very basic thinking behind this filter. Filter says, hey, if it's good, let's have more of it. If it's bad, let's have less of it. If it's really bad, meaning there's no signal there, don't let anything go through. So that's the mystery behind all of this. Why does it end up being that way? Now the question that I have for you is and you think about before you answer, is matched filter an ideal filter? No. Well, how does the ideal filter look like? Ideal filter would have flat response here, flat magnitude, and linear phase. Remember, that's our ideal filter. Okay, so excellent. So mesh filter is not an ideal filter. So what does that mean? Is your signal distorted as it goes through the filter? Yeah. Because remember, for ideal filter, the whole purpose behind the ideal filter is I take all of these sinusoidals and I build my signal. The ideal filter must not disturb the fine relationship between sinusoids, right? You know, however they come in, that's how they need to come out, right? So that's why their magnitudes are preserved through the linear response, and their phases are preserved through the constant magnitude response, and phases are preserved through their linear phase response, right? So that's ideal filter. The matched filter says, forget about preserving the signal. I want to maximize signal-to-noise ratio. So those sinusoidals that have good signal-to-noise ratio, let's amplify those guys. In the areas where there are sinusoidals that have poor signal-to-noise ratios, I'm going to attenuate those guys. So it will disturb the relationship between the sinusoidals. So if I put square pulse into the matched filter, I'm not going to get square pulse at the output. I'm going to get triangle. So the signal at the output of mesh filter is not going to look at as the signal at the input to mesh filter. But that's not what the objective here. Remember what the objective of the digital receiver is. I don't care of preserving the shape. I need to decide what has been sent. So if you send me a square, and if I get a triangle that's positive, as long as the triangle is above the noise, I know you're sending squares, but at my decision point, the triangle is high, the noise is low, so I decide it's a positive square, right? And then you send me negative square pulse, and I get the negative triangle. So as long as the position when I'm making the decision, my signal-to-noise ratio is large, I cannot confuse this negative triangle with a positive triangle. So at the output of the meshed filter, your signal does not look anything like it was at the transmission. But at a point where you sample and in which you make the decision, your signal is high, your noise is low, and your chances of making a good decision on what has been sent increases. You're not in the business of preserving and reconstructing what has been sent. You are in the business of deciding what has been sent. So you're trying to maximize your decision power, not necessarily reconstruct, because once you make a good decision, you regenerate the signal perfectly without any noise. Okay? All right, so, okay, so let me just close this by, let's do signal-to-noise calculations here based on our, ability to do that in a frequency domain and see if we get back this result. And this would close the loop, kind of go full circle. So, calculation of the signal-to-noise ratio in the frequency domain. Okay, let's look at we say ys of t. That's the part of the signal that comes. Remember, that's that sample of a signal after you filter. There's a ys here, capital T, and then also ym of capital T. And then signal-to-noise ratio is defined as the ratio of the two. So I should kind of say here S of n and the output is ys of t squared, defined by expected value of yn squared over capital T. Ys of t is a inverse Fourier transform of y s of f, and Fourier transform of the output is your s of f times h of f, right? But in our case, since h of f is match filter, this is Fourier inverse. Sorry. Is an inverse Fourier transform of s of f times s of f complex conjugate e to the minus j 2 pi f t. Right, so that's my the ys of t. At the sample time, t equal to capital T, at the time where I sample, ys of capital T is going to be f. Let me just rewrite it. So it's going to be integral from f goes from minus infinity to plus infinity. This 2 is magnitude of f of f, s of f squared, right? S of f times s of f complex conjugate is magnitude squared. Then I have here e to the minus j 2 pi ft times e to the j 2 pi ft when t is equal to capital T df. Right, so because I'm putting, maybe I should do this, ys of t and then this t. So this is this ys of t. And when I sample, then I have, I can maybe rewrite this one more time. F goes from minus infinity to plus infinity. S of f, magnitude squared, e to the minus j 2 pi f capital T minus t d. Right, so that's my ys of t, the output of this filter as a function of time. At the sample time, t is equal to capital T, so ys of capital T is going to be integral when f goes from minus infinity to plus infinity, s of f, magnitude squared df. What is this? These two cancel, right? When capital T is equal to capital T, this becomes equal to 1. So what is this? Energy. Energy of my signal. So when I'm sampling here, ys is the energy of the signal. The value of that sample is whatever is the energy of that signal. Let's look at the power of the noise. Power of the noise I can call it Pn, is going to be integral when f goes from minus infinity to plus infinity, power spectral density of the noise times h of f magnitude squared df. This is what we know about random processes. You take the filter magnitude squared times the power spectral density of the input. That's your power spectral density of the output. You integrate the area on the curve, you get the power of the noise. So in our case, this is n0 over 2, integral when f goes from minus infinity to plus infinity. H of f, so this is s of f squared df. Right? So this is equal to n0 times, what is this? Same thing, right? So this is n0 epsilon s over 2. So my signal to noise ratio at the output is going to be ys squared of t divided by this power of the noise. So in our case, this is epsilon s squared divided by n0 times epsilon s over 2, which is 2 times epsilon s over 0, which is what I should get. Right, so that's our famous result. Okay? Any questions? Go ahead.
Are you making any assumptions there to make that work out?
No. No, this is true always, right? This is, I cannot emphasize that more. And the reason why I'm emphasizing is because, you know, there's a lot of stuff I talk about, and a lot of stuff, even though I say it, it's always what portion of that you guys remember, right? So I remember when I was sitting where you are now, I would always think, but does that hold always? Was there some assumption that this, can I use that universally? And that's why I always try to emphasize, if something is true always, I make sure I say it a couple of times. This is true always. So whenever you're sending a signal and you're demodulating it with a matched filter, the output signal to noise ratio is going to be equal to that. Now, what is the catch here? Epsilon s changes as a function of what signal you use, right? If you use energy of the signal, is going to be different if it's triangle, whatever, square, because it's area under the curve. But the general expression is always going to be true. 2 epsilon s over n0 if you're demodulated with mesh filter. And furthermore, that's the best you can do, right? So even though, you know, I kind of derived this, have no doubt in your mind, 99.9% in digital communication, you're going to put the mesh filter there. So all of our communication demodulates using a matched filter. Right? And this is output signal to noise ratio. Okay? So now, we have finished the first part. The first part is demodulation. I have R of t, and I translated this into vector. How did I translate it? I translated using mesh filter, and I know what the signal to noise ratio is. What I need to wrap up next lecture is how, based on this signal to noise ratio, I calculate probability of error. That's kind of the end of this introduction to communication theory. This is by somewhat starting point in the taking of the digital communication. Fortunately, no homework because we're getting close.
No time.